Alright, so we're starting things off from the top and we're taking things from a past paper. You would have seen this past paper or this question within the Google Classroom under the tab. What's that called? I don't It's a BMED Past paper and this is from 2017. Alright, now is it 2017? Let me double check. Oh, wrong place. BMED Past paper taken from 2016. Alright, and this was the first question on the mechanical drawing paper, if that makes sense. Now it outlines that the figure that you're probably seeing in the background there, that's this figure here, and you should be able to see this on the thing. Now if you remember what this is, so this is basically a force diagram basically. So it's showing you think about this like a structure, and with RA here and RD here, or whatever letter that is. Alright, you can think about that like think about your house, right? Those endpoints might be a wall, or those endpoints could be like the two ends of a bridge. Those endpoints could be just about anything. Alright, and you can see they give you the measurements. And then on this structure here there are some different loads, aka these number here, and they're pointing to an exact location. Now whenever you see them pointing at an exact location here, all they're saying that is this is a point load. So this specific force here, which is the 10 millimeter, is directly acting 6 meters away from RA here. Likewise this 20 kilonewton here and this 30 kilonewton here. Now here the question, it says that figure 1 shows a simple supported beam, simple supported, as you can see from RA and RB, with 3 concentrated load of 10 kilonewton, 20 kilonewton and 30 kilonewton. Alright, and here they wanted to find graphically the magnitude of the reaction RA and RD, and then after you're going to verify this reaction that you have just graphically represented analytically. Alright, meaning that you're going to do the calculation. Alright, now for the graphical method, because it requires a bit more work, 15 marks, and for the analytic version, which is you doing the calculation, that's 5 marks for a total of 20 marks. Alright, now if you're going to be doing this in AutoCAD, the first thing that you want to do is just to simply quickly redraw these here. So all you'll do is just draw a line that measures 6, 7, 5 and 3. Then after you identify these point load, you could pop those dimensions in and all that stuff, and then we calculate this by the graphical method, or we determine it using the graphical method. And that's what we're going to be doing now. I'm going to be going through the process. I'll be running off my mouth a bit. Alright, please know that this is also being recorded, not just for you but for some other persons, because I believe some other persons should be joining today. Alright, whether they miss it or not, at least we capture the information here. Alright, so here I have my image in AutoCAD as usual. Now I'm just going to quickly draw I'm just going to quickly draw what I have here. So I'm basically going to be drawing 1, 2, 3, 4 lines. So I'm going to draw one horizontal line, 6,000, because 6 meter is 6,000 millimeters. I'm going to draw another one from there. Let me turn on this here. Another 7,000. Then I'm going to continue for another 5,000. And then finally 3,000. Now from those points I'm going to be drawing up some vertical lines. So I'm just going to be using dynamic tracking here to just quickly produce this here. And in the exam, if they give you a paper, you can always do this on paper using your ruler. So on the day, don't forget your ruler if anything. That is if you do not want to do it in AutoCAD, or if they even place you guys in the IT lab. I don't know what they're going to be doing this year. Alright. And you can add your labels. Not really necessary, no, but let's just add them nonetheless. So it's 10 kn. It's a bit too small. Let me just scale it up a bit. Say 10. I want it to be 1. Alright, so that's 10 kilonewton. Let me just copy it to the other locations. 1 there and 1 there. So one is going to be 30. One is going to be 20. Alright, and then let me just add the annotation down here, which is RA and RD. A, and this A here is a lower, is a that thing there, whatever that is. Then we have RD over to our right. So it's basically reaction A and reaction D. That's what the R is for, which is just aka a fancy word for the force that is acting there. Alright, so this is it in a simple form. If we're going to add some dimension just for clarity, so we have from here to here, we have from here to here, and let me continue, we have here and then here. Alright, so we have all our reactions there. As you can see, 5,000, 7,000, 6,000, and 3,000. Alright, so to determine this here, we can do a further labeling, such as using Bow's notation, and that is just us highlighting the spaces between the forces. So we call here A, B, C, and we can go to D. So let me do that as well. So we're going for our notation here. So A, let me copy it to my right. Let me turn on this here. So we have there, and yes, we would have one there. So this would be B. And as you can see, this takes time. So it's the reason why I say if you can do it on the paper, even better. So you just get a ruler so you can work out your scaling and all that stuff. Alright, so sometimes you have to choose your battles. C, D. Alright, so we have A, B, C, and D there. So it's now time for us to utilize the graphical method to determine the reactions at RA and RD. Alright, now the first step is to first create the polar polygon. Alright, and the polar polygon will basically be representing each one of these loads here. Alright, so we have this here, the 10, the 20, and the 30. So what I'll be doing to the side here, or to my right, I'm going to be drawing a line down, and this is where the scaling come into play for you guys. You determine what scale you're going to use, but for me, I'm going to say that for every 1,000 kilonewton, I'm going to make my line I just want this to be appropriate. 10. I'm going to say for every 1,000, I'm going to make my load line 5 or 0.5. 0.5. For every 1,000, I'll make it 500 millimeters. That's what I'm going to do. Yeah. So for every 1,000, I'm going to be making it 500. Alright, so in this case, 10,000 will be equal to half that, which is going to be 5,000, because I want things to be a bit more proportional. Then for the second load line, which is the 20 here, it's going to be 10,000. So 1, 2, 3. Oh, that is 1,000. No, 10,000. So 1, 2, 3. Enter. And then finally, half of 30,000 is 15. 1, 2, 3. Alright, enter. Alright, cool. Then I'm going to identify my pole, and my pole is going to be somewhere over here. Personally, for me, I like to make mine smack in the center of this here, but I was told that it was random, so you can make yours random as well, but I'm going to make mine like this. Alright, I'm then going to be connecting lines from each one of these points to the pole, which is over here. Let me copy this, and then I just add a label so you see what's going on over here. So this is the pole. Let me just add a point there. Point. PT. Enter. Here. Okay. Get rid of this now. So we have point B there. So this is our pole. Alright. Pole, aka point O. Alright, now from each one of the points on this line here, we're going to be drawing a line. So for example, here and here as well, all those points, and then I'm going to go through and label my line. So everything is going to the pole. Just finding that rectangle portion there. That's how I know that it's the end of the line. If I'm seeing a triangle, it means that that's not the end, it's the midpoint of a line. So I need to be seeing rectangles. Not seeing it that way, so let me try hovering over this here. See if I can see. Yep, here's one here. Alright. Let me just change the color so you can see a bit better. So I'll probably make this like purple or so. And this one can be, I don't know, maybe this color. Alright, so we have those points there. We can label them now, and we're labeling them based on the annotation that is here. So we're starting with A, alright, then point B, and we're making our way down. Alright, so that's what we're going to be doing. And in this case now, the letters are going to be in common letters. I don't know if they give marks for these type of stuff, but who knows. Hence the reason why I say, if you can do this on paper, it will make things a lot easier for you in terms of like the amount of time that it will take to do all of this here. But to each his own. Point there, and a point down here. Alright, so we're going A, we're going B, we're going C, and we're going D, which is the last one. Alright, so now once all those points are labeled, you can also dimension these as well, just for additional clarity and just for you to kind of understand the scaling and all that stuff. Alright, so this here is our load line. So what is left for us to do now is to know we're going to be doing our funicular link polygon. Alright, and this will allow us to find the equilibrium, alright, as well as the equilibrant. Alright, so let's now do that. So we're going to start by first projecting lines down from, and I'm going to use a fancy color here. We're going to be projecting lines down from everywhere there is a point or a force acting on our beam here. So for example here, RA, I'm definitely going to be projecting a line down. The length of it, you can make it as long as this here. Alright, because we only need to do the reaction. Alright, so once that is out of the way, we're just going to copy this one here and we're going to place it at everywhere there is an a load or a point acting there. That one didn't snap where it's supposed to snap. So let me move it. Alright. Alright, now once that is out of the way, it is time for us to now copy these diagonal lines here that runs from the load line to our pole. And we're going to start by first copying point A here, our PO line. I'm calling it PO because the pole is called point O and here is point A. So between A and O, line PO, just like in maths. Alright, and I'm going to put it right there. Alright, now remember, here is what this represents. Alright, basically here. Alright, so anything that falls outside of the line, what are we going to do? We're going to get rid of it. So we're trimming away that. On the day of the exam, if you're doing paper, if you're doing this way, you choose. Alright, now the next step is to move on to the other load point, which is this one here. So I'm going to copy. I'm going to place it where? Right here. Again, once it goes beyond this zone, if you want to call it that, get rid of that. We're now at where? C. So let's copy C and place it right here. I think I snapped to the wrong thing.
Sir.
P, enter, grab onto this, place it right there. Once it goes beyond the point, let's trim that out.
Sure.
And then finally, we have the final one, which is line DO. So we take DO and we slap it right here. Alright. Then now we trim away the excess. Alright. Now we basically almost finished, if you want to call it that right there. So now once that is in place, the next step is to draw our EO line or EO line. Now our EO line is basically going to be, and the EO, the EO is actually the equilibrium line basically. And it is a line that runs where? From here, R is there to here. So we're basically moving from X to Y. Let me switch the colors of this here to probably something else. Like no. Oh yeah, let's just work that. Alright. So this is the EQ line. Now to find out where on our E or EQ line, where on our load line it is going to fall, we're then going to copy this line here that we just produced, and we're going to place it where? Right on our pole. Now you see, anywhere it touches the load line, that is your equilibrium point. Alright, and I'm going to put a letter there, and this is going to be called point E. So this is point E for our equilibrium. Alright, so let me switch the line type on these here to something that is broken. I think broken. Do we have anything that is broken? Foundation. Alright, cool. And then we probably can change this to something else that is solid. Hatch. Yeah. Alright. So we have identified our EQ. Why do I keep on saying EQ? But EO line. Alright, and it's on there as well. So it runs from point X over here to point Y. So it's moving along this axis here. Now the next thing that we're going to be doing now is to find the equilibrant point. So we find the equilibrium point. We now need to find the equilibrant point. Now the equilibrant point is easily found by simply extending or filleting these two end lines together. Alright, so if you did this using your on paper, then you just simply place your ruler against here and simply draw a line, a random line, just draw it to a certain length. Then you do the same thing on the other side and anywhere the two lines intersect. Alright, and for this you must understand how to create parallel lines, and this is the one. I don't know if you know how to do this using your using your set square and your ruler, and you simply slide them against each other. I don't remember if I did this in class with you guys. Alright, and you will get your parallel line. So you'll place the set square along this line here, and then you set your ruler and you simply slide the set square until it gets to over this point here. Once it gets there, you simply work the magic. Alright, so let's fillet these two lines. Alright, so you see that point that is formed there, that point there, that line there, you're going to simply draw a line from there all the way up to where the beam is. Alright, now this line here, let me change the color. This line here, it didn't change. This line here is your equilibrant line, if that makes sense. This is your equilibrant line. Alright, so you know you can label them and all that stuff. So that's your equilibrant line. Alright, now, and this, all of this here, you know, all of this here shows you the reaction at R and R, let me call this, and RD. Alright, now you simply have to use your dimension line, or your dimension tool to dimension these points here. Alright, and how are we going to be doing that? You're simply going to be doing a dimension from O, that point there, or E, to point A and to point D. Alright, now once that is all out of the way, let's go ahead and manually calculate the reaction at R, what do you call this, RA and RD. Alright, now the process is simple. All we're doing is calculating the moments about point A and the moments about point D. Alright, but first we do RA and then RD is pretty simple. So let's start that off. So I'm going to be doing everything in a text box. Everything is going to be done in a text box. 0, 2, let's make it 2. Alright, cool. Annotate multi-line text. Let's go 2. Alright, so here's what we're going to do. So moment at RA. Alright, now, so let me just write that. Moment at, and I'm going to just say at or about RA. And RA is this fancy one here. Let's see. Text is a bit small. Let me just make it a bit bigger. Probably can make everything 5. That way too big. Or what? That wasn't 5. It's 500. You know what? 10. Alright, yeah. Alright, so let's do this now. So basically what is going to happen is that we're going to be multiplying the distance from each one of these loads here, and then we're going to be summing them together. So we need to find out the sum, not the sum, the product of the distance to each one of these loads here. So for example, starting with the 10 kilonewton, we're basically multiplying that. So we're going 10 kilonewton multiplied by the load, with multiplied by the distance, which is 6 meters. Alright, and then whatever that works out to be. So 6 times 10 is 60, aka 60,000. 1, 2, 3. Then now we're going to be doing the same thing for the other point load, which is the 20 kilonewton. So we're going to be adding now. So we're going to have to increase things. So the distance now from, this is far, yeah. The distance now from point here, this load here, which is 20 kilonewton, away from RA. So we have 6 here, and then we have 7. because that's how the distance is. So 6 and 7, how much is that? I don't know. 6, 10, 12, 13. Alright, so it's going to be 13 times 20. Alright, so we're going 20 multiply 13. That's what I calculated a while ago. 7, 8, 9, 10, 11, 12, 13. Yeah, 13. Alright, so 13 times 20, whatever that works out to be. How much is that? Somebody calculate that for me.
So you're not hearing us.
Anybody have a calculator?
So can you hear us?
Don't forget your calculator on the day as well. Alright?
I'm not hearing 260. Sir?
13 times 20. 260. I'm just going to make this 60. Just for now. 260. And then now, the next...
Hey, then I'm calling him right now. I'm calling him right now.
What's going on here? Hello? So, you guys get what me not going with up until this point?
Yes, sir.
Alright, cool.
Yes, sir. Yes, sir.
So, the next number or the next load is the 30. So, it's going to be the 30 multiplied by the distance, which is, what's that? 6. It was 13, right? So, 13 plus 5, 18. 18. So, 18 times 30. How much that? 18 times 30. That's a 540. 540. Alright. So we have 540 now. So from this point now, what we're going to do is that we're going to be tallying up or totaling the product of all of these here. So we're going to the 540 plus the 260 plus the 60. How much are we getting? We're getting 800 and so we're getting 808.60. So that's what we're getting total. $860 total. Yeah, so 860. Alright. Now then I'm going to do something with you guys so you can see what's going on. Alright, so 860. Now you see, once you have that number there, the next step is that you're going to be dividing that number by the total span of the beam. And the total span of the beam is, I think we missed one, so it's, how much was it? How much was the last number? 18. So 18 plus 3, 21. So the total span of the beam, and I could have found that out easily if I just drew a dimension across here. Alright, so the total span is 21. So what are we going to be doing? To find the moments or the reaction at RA, we're simply going to be, alright, so I'm just going to write this, moments about RA. So moments about RA, moments about RA will be equal to that 860 divided by, where is my divide symbol? Divided by the span of the beam. Alright, and the span of the beam is going to be equal to, how much did I calculate? 21. Alright, now and I'm guess I'm saying this wrong to you, saying it wrong to you. The what you're actually calculating, you know, is actually the distance between RA and RD. Alright, so say for example RA was at this point here and RD was here, you'll only be including the 7 and the 5. Alright, so that's something to bear in mind. So it's based on the distance of the supports. Alright, so let's divide that 860 there. So 860 divided by 21. How much did we get? 40.92. Alright, so I'm just going to write that right here. So 40, which is equal to 40 point, I'm just writing 95 here just for that purpose. Alright, so that's the reaction at our RA. Alright, so now it's time for us to calculate the reaction. So the reaction at RD, and you know RD is that this one here, that's RD. Alright, now to find RD, alright, all we're going to be doing is that we're simply going to be taking the total load, yes, the total load, yes, so we're taking the total load. So the total load, which is basically let me do this much here, 30 plus 20 or 50, that plus 10, so 60. So the total load is 60, so we're going to have 60. Alright, and when we have the 60 there, we're going to be minusing the reaction at R RA. So we're minusing the reaction at RA, which work out to be 40.95. Alright, now you see the number we are gonna get here, so I'm going to do the maths here for you guys. I'm going to do the maths. 60.
Wait, so how you get the 60 again?
The 60 is the total load. So it is all of these load
Oh, the
that
10, 20, 30, okay.
yeah. So
So
that's
why never do that for the other side?
no, because the other side, we see, say for example, because we let me tell you something. And this is how it was taught to me in university. Alright, so I don't know the justification behind it, but it works either way. So instead of, because remember, you know, we didn't know the total amount of force, now we don't know the reaction and what go on here. So you know, we're trying to derive it based on the amount of force acting. Alright, because we didn't have to do RA first. No, we could have done RD first and simply multiply 3 meters times 30, 8 meters times 20, whatever this number here is, the 3, 5 and 7 times the 10, and then we calculate the reaction for RD from that. And then after now would still minus whatever we would have gotten here for this reaction at RD from the total force, and that would have given us RA. Alright, so it works from either ends. Alright, it's just that I start from my left to my right. Alright, it makes sense?
Yes, sir.
Yeah. Alright, so minus, so we're going to minus that 40 there, 0.95. So the reaction at RD would be equal to 19.05. Alright, so that would be the reaction at RD. Alright,
Oh, sir. Yeah, that makes sense too, cause when the way I look, you showed us a first, a different way at first, like earlier in the school year,
yeah,
and I watched a YouTube video and I was preparing for, like the last work you gave us, and the sum of it,
yeah,
the sum of the right side and the left side should be equal to the total force acting down, which is the 60.
yeah,
So this
because
way,
yeah,
hmm
because
so that makes sense.
it's engineering, you know. So you see, if for some reason, you know, if the force above is acting more than what is supporting it, you know, guess what is going to happen? The building is going to fail, the bridge is going to fail, whatever structure it is going to fail. Alright, so that is why we need equilibrium. And look at this here, and I hope this works out. If not, we're going to have to multiply this by 1,000. Alright, so let me show you something here. So from here to over here, and here to over here, where is it? Here Yeah, and if you're doing it in AutoCAD on the day, do this as well. It's just to prove your point. Prove your point. Let me see now. Here to here.
So I feel like it'd be much quicker to do it on AutoCAD though.
Really?
Because drawing with a yeah, so drawing with a ruler that would have take longer than if I just
Yeah,
draw
yeah,
straight.
yeah, you have a point. If you were just doing the calculation, the raw calculation, then 1 minute and you're done the calculation. Alright, so
Yeah, the typing, the labeling, all of that would have been the harder part,
yeah,
and
the labeling would
the
take
drawing would
some
have been
time. The
easier.
labeling would take some time. Yeah, the labeling would take some time. The labeling would take some time. Alright? But personally for me, I don't like to use scale when I'm doing these. If I'm going to do it in AutoCAD and I want to make my life easy, I wouldn't do any form of scaling. I'll just draw this everything raw with the raw numbers there. Alright? Because everything is going to be proportional anyways. Everything is going to be proportional anyways. What's this number here? 20,000. Whatever this is. 20,460. 20,460. 14,000. 14,000. 60. 14,360. Alright. So as you can see here, basically one side of the thing every on one part. Alright. And you can think about this like if you have a ruler and you're trying to balance it you have it flat horizontal and you're trying to balance it at on your finger, right? Now depending on how the weight is distributed on the ruler, it might lean to one side or lean to the other side and fall off. But when you get to that point where the forces on either side is equal, you'll find that the ruler starts to balance on your finger. Alright? So it's kind of something similar to that. Without overcomplicating things. Alright? So in the exam, if you see anything like this, do this. Alright? And you're sure of your marks. Even if you don't put in all the labels and all that, you're sure you're going to be getting at least 18 out of it. I'm assuming I don't mark BMED papers. Alright? Person like other teachers, maybe like Mr. Tate. I think Mr. Tate marks BMED. Alright, so this is what you'll do for something like this. Do the manual method and you do this here. Alright, please bear in mind that these numbers here, multiply them by 1,000 if you're going to be messing around with the numbers because of the units. Alright, yeah, that's it. Alright, so this is this portion here out of the way. Let's see what else is on this thing here. Let's see what else is on it. Let's see what else is on it. Oh, we have this here.
And so that answered the 2 parts.
2 parts?
There was 2 parts to the first question that answered both of them.
Yeah, so this is the graphical method. Over here is the graphical method. Alright, and over here is the analytic method. Analytic means that you do the calculation manually. Alright.
Okay,
Yeah. So
so you
graphical
have to put a
method.
dimension.
Eh?
Wait, so that what that name again? That thing to the right, that symbol to the right.
This part here.
That
This part.
yeah.
This is
So
the polar polygon.
so you have to dimension it to show
Oh
that
no, not really. No, not really. Not really.
alright,
But
cool.
you can. Alright, so as I would recommend you doing everything first, starting out, ensure that you have everything before, and then after now you can go through and you do your labelings. You go through and you do your labels. Alright? Because you know time ago sticky in the exam. The time ago it's going to be a bit sticky in the exam, the timing. 10. So you just go to, so this is the polar polygon. And as you know, you know what polygons are already. So this is a polygon, because this is basically a triangle, so it's a polygon. Alright, and the pole part of the description is basically here that they call pole. Alright, and this one here is the funicular link polygon. Funicular for you know what's a funicle, right? If you did probably chemistry or physics, or if you ever see somebody pouring like oil or something in a bottle, you see they put a little thing in the thing, like a funnel like a phone. Funnel, yeah, funicular. Hence the reason why you see how the names kind of link up. So phone, that the whole thing there, and the link is in relation to linking this polygon over here. So you link this polygon to what is over here. Funicular link polygon. Alright?
Alright, sir.
Yeah, man. I hear a beep a while ago.